So the next one will be again from Stephen Hanham from the Birmingham University. Stephen, are you there? Yeah. Thank you for accepting the invitation. And Stephen will tell us about sub-wavelength biosensing in THz domain with metamaterials. That is a kind of really hot topic. Thank you, Stephen. Please start.
Great. Thanks, Vincenzo. Thanks for the introduction, and thanks for the opportunity to speak today. Okay, so as Vincenzo said, I'm talking today about sub-wavelength biosensing in the terahertz domain with metamaterials. So the outline for my talk, I just want to begin my talk by talking about some of the plasmonic surfaces that we've been developing for performing terahertz sensing. So the idea here is that we want to develop surfaces which support strongly confined waves, and that'll allow us to sense objects or structures that are smaller than a wavelength, okay? In the second part of my talk, I want to talk a bit about how we've been developing these high quality factor resonators as a platform for developing, for detecting bioliquids. And in the third part, I just want to talk a bit about some of the microwave sensing for cell detection we've done, okay? Again, using metamaterials to enhance our sensitivity. Okay, so one of the problems with applying terahertz towards biological sensing is that we're working with quite a long wavelength, okay? So some of the objects we'd like to sense, such as biological cells, are much, much smaller, okay? So a wavelength might be hundreds of microns, but the cells that we're interested in might be only 8 microns, okay? And so as we know that detecting objects in the far field, we're limited to around half a wavelength, okay? So that means that we need to adopt these near field sensing techniques, okay? And by the adoption of these near field sensing techniques, we can apply terahertz sensing to the micro and nano science fields, okay? And so the two methods I want to talk about today for improving our terahertz sensing sensitivity is the strongly confined plasmonic waves, as well as using high quality factor dielectric resonators. Okay, so let's start by talking about some plasmonic surfaces. So typically when we think of surface plasmons, we typically think of the optical part of the spectrum, okay? And we typically think of noble metals, all right? Now, as you know, these surface plasmons, they exist at the interface between a dielectric and a conductor. And they have this very nice property that they're able to confine and enhance and guide light well below that diffraction limit. Now, it would be nice to be able to have those same properties in the terahertz domain, okay? Now, if we look at the formula for the plasma frequency of a material, we see that the plasma frequency is proportional to the square root of the electron density, okay? And so what we can do is that by adopting semiconductor materials, these are materials that have a much lower electron density, we can shift that plasma frequency down from the optical part of the spectrum and into the terahertz, okay? And so just shown on the right here is the permittivity, the complex permittivity for a particular semiconductor, indium antinide, okay? And it has this nice property that its plasma frequency is in the terahertz band. Okay, so the first thing we did was to go ahead and create some arrays of dipole and bow tie terahertz antennas, which were made from that indium antinide, which was grown on a gallium arsenide substrate, okay? And so those micro antennas allowed us to have this efficient coupling from the far field to the near field, okay? So essentially they confine the electromagnetic radiation, the terahertz radiation, into that small gap between the tips of the bow tie, okay? And so we can then use that enhanced electric field for performing sensing. So we could functionalize the surface at that point, or indeed we could introduce a microfluidic channel to flow a liquid through that hot spot, okay? So just an example of how much improvement we can get. So shown here is a comparison between a metallic or gold dipole antenna and an indium antinide semiconductor antenna, okay? And so, well, semiconductor antenna, which exhibits a plasmonic response, okay? And shown in the second row here, we can see a plot of the electric field for both antennas. And what we find is that the enhancement of the field for the plasmonic antenna is actually larger than the metal antenna. Okay, so keep in mind that we're operating the terahertz regime where metals are still fairly conductive. Okay, but despite that fact and that lightning rod effect you get in metal antennas, the plasmonic antenna gave around about a 200 times improvement in the enhancement of the electric field in the gap between the two dipoles. Okay, so that shows you the improvement we can get using plasmonic antennas. Okay, now another structure that we looked at soon after that was looking at these indiumantinide touching discs, or sometimes called kissing discs. Okay, so essentially this is two discs that are brought into very close proximity and even touch slightly. Okay, and we're interested in these structures because they potentially offer broadband concentration of terahertz radiation. Okay, and so they can hopefully, by concentrating the energy in those gaps, we could overcome that large size mismatch between our terahertz wavelength and the biomolecules that we're interested in. Okay, and we also had a second motive for looking at these structures, and that is to prove certain aspects of transformation optics. Okay, so transformation optics make some certain predictions, but it's hard to verify some of them in the optical part of the spectrum. Okay, and so by adopting the terahertz part of the spectrum, it makes it somewhat easier from a fabrication perspective. Okay, so the particular work we were talking about was this transformation work, this famous paper by Pendry and Meyer, where they showed that if you start from a broadband structure, like a plasmonic waveguide, and then apply a transformation, we can come up with these structures which have a broadband response, okay? And they tend to be quite singular structures, okay? Such as that touching disc structure as shown in the top right here, okay? And so we're interested in seeing whether this theory is accurate with real structures that we fabricated. Okay, so just shown here is the simulations of these touching disc structures. And one of the things you can see is that as you bring those discs closer into touching and then begin to overlap, we get this broadband response, okay? So the theory from transformation optics predicts that there could be this very, very large spectrum of modes, the structural support for that singular structure. However, in practice, it's difficult to realize that singular structure, but we were able to show that you have this enhanced broadband response, okay? And then we went ahead and fabricated these structures and used terahertz time domain spectroscopy to measure the absorption cross-section. Okay, and we're able to show that due to the excitation of these additional modes, we could get this relatively broadband absorption cross-section. Okay, and you can see from these plots in the bottom right here that we're able to concentrate that field down to a very, very small area, so sub-micron, which is quite small when you consider how long the terahertz wavelength is. Okay, so that was using semiconductors to get a plasmonic response. Now there's another approach to doing that in the terahertz domain. Okay, so let's now consider a flat metal sheet of metal, and we've known for some time that a flat sheet of metal will support a Sommerfeld or a Zenit wave. Okay, however, that's a very delocalized sort of wave. Okay, and we're sort of operating in a regime where we've got very, very high conductivity in the terahertz domain. Okay, so we have this, you can support this delocalized wave. Now, Pendry showed in this science paper back in 2004 that if you take that same sheet of metal and you cut corrugations into it or put holes into it, you can actually engineer a dispersion characteristic corresponding to a very confined wave, okay? And so what happens is that the electric field of your wave, shown on the right here, is able to penetrate partly into the metal, okay? And so you end up with a dispersion characteristic that's very similar to your plasmonic wave, your surface plasmon, okay? And so that led to the name of a spoof surface plasmon because it has plasmonic-like dispersion characteristics. And so shown in the bottom right here, we can just see the electric field distribution for that confined wave propagating along a corrugated surface. Okay, so we're interested again in testing that. And so we fabricated this corrugated metal surface, okay, shown in the top left here, just metal over a layer of photoresist, gold in this case. And we went ahead and used time domain terahertz spectroscopy again to excite that spoof plasmon mode, okay? And because of its high K vector, we had to use a technique to couple into that wave. And the way we did that was to use these very sharp surfaces, these razor blades, in fact, where we diffracted an incoming terahertz wave that then coupled with that spoof surface plasmon. Okay, and then we used the second razor blade to couple that energy out again to then measure the transmission. Okay, and using that approach, we're able to map out the dispersion characteristics for that spoof plasmon wave, as shown in the bottom left here. Okay, and so that worked very nicely, and we're able to fully characterize the wave. Now we took that one step further by using that surface for forming liquid sensing. Okay, so those corrugations in our metal surface actually make very nice microfluidic channels. And so we're able to flow liquids through those channels and then look at the resulting change in dispersion characteristics. And so shown on the left here, we have those dispersion characteristics for a range of non-polar liquids. And we can see that the properties of those liquids, the real part of the permittivity, in fact, modifies that dispersion characteristic quite strongly because of the strong interaction between that surface wave and those liquids. Okay, and on the right we can see that we've measured the change in transmission, which corresponds to the attenuation due to those liquids, and we can see that we're also able to map out the attenuation, which is primarily due to the imaginary part of the permittivity of those liquids. Okay, so it allows us to characterize the full complex permittivity of those liquids. Okay, so another surface that we looked at was this domino surface. Okay, so again, it's that corrugated metal surface, but here what we did was we shrunk the lateral dimensions of the surface just in a small point where we wanted to perform sensing. Okay, so again, this will support that same spoof plasmon mode, but note there's no cutoff as you reduce the lateral dimensions. Okay, so the reason that we're interested in this surface, I should say, was that we were interested in sensing biological cells. Okay, biological cells which are being flowed in a carrier liquid. All right, so what we did was reduce the lateral dimensions down to around the dimensions of that biological cell. And so then we measured the transmission through that spoof plasmon surface. Okay, and what we were able to show was that the transmission transmission through that spoof plasmon surface depended highly on a particle that was flowing through the liquid. Okay, so the particle in our case was a biological cell, and what we found was that close to the Brillouin zone edge, where that spoof plasmon mode is strongly confined, we had a huge change in the frequency, sorry, the transmission versus frequency for that spoof plasmon mode. Okay, so here you can see that just the particles changing its refractive index from 1 to 1.7, okay, corresponding to the particle being there or not being there, we had a change of over 100 gigahertz, which is quite a large change in frequency that we're very easily able to measure using terahertz time domain spectroscopy. Okay, so this made a very nice sensing platform for our cell sensing project. Okay, so that was the spoof plasmon surfaces that we've been looking at. I wanted to change topic slightly, and that is to look at this approach where we use high quality factor resonators for performing sensing. So it's sort of an alternate approach. Rather than using a strongly confined surface wave, here we're taking advantage of a very high Q resonance to perform our sensing, which will hopefully increase our sensitivity. Okay, and I just wanted to briefly mention the application we're interested in. I know I won't go into too much detail because I know this is a Metamaterials conference, but we're particularly interested in detecting biological cells and a particular type of cell, what's called a circulating tumor cells. Okay, and so these are cells that have detached from a primary tumor site in the human body and into the peripheral stream. Okay, and so the thing to note about these cells, other than being important for a range of medical applications, is that they have a different morphology. Okay, they can often have an irregular shape or different subcellular morphology, and that allows us potentially to detect their difference as compared to healthy cells. Okay, and there's already a range of approaches that exist in the literature, such as molecular tagging or physical separation techniques. Okay, and so we're interested in seeing whether terahertz could be used for this particular application. And there was some reason to think that it would be useful. Okay, so just briefly, we know that at RF frequencies, we have problems with ionic diffusion and membrane polarization, which can screen the field from seeing inside the cell. Okay, however, at the terahertz, those membranes are somewhat more transparent. Okay, and so you tend to see the tail end of the dipolar polarization of the water molecules. And so what that means is that it's going to be very sensitive to the presence of water or the absence of water due to other non-aqueous components inside the cell. Okay, and so that got us interested in asking the question, well, what can we do with terahertz sensing of individual biological cells? Okay, so that led us to looking at ways that we could increase our sensitivity. And as I said, we were interested in looking at and using resonators for performing this. Okay, now there's a number of examples in the literature, particularly at optical wavelengths, for using very high quality factor dielectric resonators for sensing. And so one example we have here is where they used a whispering gallery resonator, for example, to detect a single protein molecule. Okay, and they made this nice whispering gallery resonator with a Q of around 10 to the 8. Okay, now the problem is if we want to do the same thing at terahertz, is that our wavelength is 1,000 times longer. Okay, and so your resonant motor volume will be 1,000 cubed times larger potentially. Okay. We have a second problem in that we're not able to make such high Q resonators because the materials that we typically use, their loss tangents or their dielectric loss is nowhere near as small as they are in the optical part of the spectrum. Okay, and so that makes it much, much harder to realize these really high Q resonators in the terahertz band. Okay, so what we started to do was to develop high Q resonators, and the approach we took was to develop these photonic crystal resonators. Okay, so taking ideas developed at optical wavelengths and bringing them to the terahertz domain again. Okay, and so the particular resonator that developed was the well-known L3 resonator. So here essentially you have a dielectric material which has a triangular lattice of holes in it. Okay, and those triangular lattice of holes create a band gap which prevents the propagation of waves in that substrate material. Okay, and the way that we can create a resonator from that is to emit 3 holes from that triangular lattice, which creates a defect in the lattice. Okay, and that defect supports an electromagnetic resonance. And we can then couple to that resonance using these defect waveguides shown on the left here. We've emitted, partially emitted a line of holes. Okay, so it allows us to couple into the defect and then back out again. Okay. So we went ahead and made these at 100 gigahertz. And the way that we did that was to start with high resistivity silicon. Okay, so important that we use high resistivity silicon because it's got very low free carriers, which can be a real problem at terahertz frequencies. And so high resistivity silicon is one of the lowest loss materials at terahertz, has a loss tangent around 10 to the -4. Okay, and so we used deep reactive ion etching to create those holes in a 0.5 millimeter thick silicon wafer. And we implemented our photonic crystal resonator. Okay, and so just shown here is where we're measuring one, but rather than using lasers and photodetectors, here we're using a vector network analyzer, which uses a metal rectangular waveguide to excite those defect waveguides, which then couple into our defect resonator. Okay, and we're able to demonstrate Q factors of around 10 and 20,000. Okay, and that's primarily limited by our silicon dielectric loss. Okay, and so we can't do much better than that at room temperature. Okay, we also made, just briefly, we also made some 1D photonic crystals. So these are what's similar to the nanobeams that you get at optical part of the spectrum. But these are essentially consist of a dielectric slab waveguide, which has a series of holes, as shown in the bottom left here, where that series of holes again creates a photonic band gap. And then we introduce a defect by varying the radius of the holes in the center of that beam. Okay, and so note that we've suspended that microbeam by these suspending struts at the left and the right hand side. Okay, to electrically isolate it from its surroundings. And using this approach, we're able to get Q factors around 12,000 at 100 and 200 gigahertz. Okay. Now, having developed these high quality factor resonators, we're interested in using them for measuring liquids. Okay, and so the way that we did that was to introduce some microfluidics. Okay, and so we used a very, very fine microcapillary to flow liquids through that defect resonance of the photonic crystal resonator. Okay, so it allows us to introduce that liquid into the electromagnetic field associated with that defect resonance. We then monitor the changes in the resonant frequency and the quality factor of our resonator as the liquids are flowed through the resonant field. Okay, and what we were able to show was that due to that really high quality factor, we're able to achieve interaction volumes of around 4 nanoliters. Okay, so sensing very, very small quantities of liquids. And the nice thing about this approach is that it has high levels of integration. So we think this could be built into a system with the microfluidics built in into the chip itself. Okay, so we went ahead and measured some liquids. And so shown on the bottom right here are a range of liquids. So we've got 2-propanol, ethanol, methanol, and a range of ethanol water solutions. And what you can see is that as we flow those liquids through the photonic crystal resonator, we get a change in its resonant frequency and its quality factor. Okay, so the change in resonant frequencies is primarily related to the real permittivity, and the change in quality factor is primarily related to the imaginary component of the dielectric constant. Okay, and so you can see that we're able to distinguish between a whole range of liquids purely based on their complex permittivity in the terahertz band. Okay, so having done that, we were interested in being able to quantify that complex permittivity of the liquids that we were interested in measuring. And the way that we did that was to use a simple electrostatic model which describes the field inside the microcapillary, and then apply perturbation theory, which relates the change of that electrostatic field with the change in the resonator's resonant frequency and quality factor. Okay, so that gives us this nice connection where we can directly estimate the complex permittivity of our liquid. Okay, so we went ahead and measured a number of different bioliquids at 100 gigahertz. Okay, and so shown here is this table where we've characterized a few of those liquids. And as I said, we're interested in measuring human blood. And so here we have plasma from human blood. We're able to measure its complex permittivity. Okay, we're also able to measure some red blood cell suspensions and some white blood cell suspensions. Okay, now thanks to the high Q quality factor, we're able to measure down to around a 40 cell suspension. Okay, so we didn't quite hit the single cell sensitivity. We're able to get fairly close. Okay, around 40. And we think with our next generation of photonic crystal that we're currently working on fabricating, we can get that down to the single cell sensitivity, okay, which is quite impressive given the long wavelength at 100 gigahertz. All right, so that was a work at terahertz frequency. Now we also had a similar project which was working at microwave frequencies, okay, and this was again using a resonator approach where we combined a high quality factor dielectric puck resonator, okay, shown in the bottom left here, which is housed inside a copper cavity to reduce the radiation. And then we combined it with a dual split ring resonator, okay. So what we did was tune the two resonant frequencies of those two resonators so that the two resonators coupled together. So we have a coupled resonator system, okay. Now, the advantage of that is that it combines a high quality factor structure, the dielectric puck resonator, with a structure that has strong field confinement, the dual split ring resonator, okay? And so by exciting them such that the resonant frequencies align, we're able to concentrate the field in the dual split ring resonator down to that small capacitive gap between the metal rings, as shown in that middle figure there, okay? And then what we did was introduce a very fine microfluidic channel which flowed through that gap in the two split rings. Okay, and so that allowed us again to flow our liquids through our resonator and measure the change in quality factor and resonant frequency. Okay, and so again, here we're measuring a volume which we estimated around 200 picoliters. So very, very small sensing volume. Okay, and so we went ahead and flowed some biological cells through that structure, and we monitored the change in amplitude and phase of the resonator at the resonant frequency, and we're able to detect single cells as they flow through that small gap in a dual split ring resonator. Okay, and so the nice thing is that here we're only measuring at one frequency. We can do it very, very rapidly using our electronic system. Okay, and so you could essentially think of this as a flow cytometer, but for the microwave part of the spectrum. Okay, and so the reason that we've been able to do this is because our split ring resonator allows us to confine that field down to a very, very small sub-wavelength volume. Okay, and just shown here is some results for flying some real cells through a resonator. And on the left here, we have mouse myoblast cells, where you can see that we're able to detect the presence of those cells due to changes in the phase and amplitude of our resonator. And on the right here, we have some human mesenchymal stem cells. Okay, and again, we can see we're able to choose that. And again, we're still performing some optimizations to the system to try and improve its sensitivity. Okay, and try and improve how well we can distinguish between different cell types. Okay, so I'll just finish up with some conclusions. We're developing terahertz semiconductor and spoof plasmonic sensing surfaces, okay, for a variety of sensing applications in the terahertz domain. I also showed some high quality factor terahertz photonic crystal resonators that we've developed for sensing of solvents and cell suspensions and bioliquids. And finally, I finished with a microwave coupled resonator device, okay, which is able to use split ring resonators for enhancing our sensing sensitivity. And so hopefully I've shown you that by integrating these microfluidic systems with our sensing surfaces, we're able to sense nano-litre volumes of biological, toxic and explosive liquids. Okay, and our future goal is looking at this, continuing this development of a lab-on-chip device for circulating tumour cell detection. Thanks very much.
Thank you to you. Very, very interesting talk. And I see that there is already a question that is, thank you for the nice presentation. In the spoof surface plasma experiment, what was the concentration of the particles? And did you consider a mixed fluid or particle using resonance effects?
Okay, so we were primarily interested in biological cells. So we were just diluting them down to a single cell at a time, okay? Because two cells going through the resonator, through the surface at the same time would create some confusion. So just interested in a single cell sensitivity. The particles themselves don't support that we're interested in looking at, certainly don't support resonances because they're quite sub-wavelength. But I guess there is the potential that you could look at other particles that have a resonance. Okay.
And if there aren't other question, I will ask you one. I understand the idea that you need a structure with a really high Q factor, so you can, I mean, the part that you can focus, you have long lifetime of your model, whatever. But would be not interesting to have a different structure with different, that they have a really good quality factor at different frequency. So you could make a kind of spectrometer, because I think that if you could have a spectroscopy of biological liquid, maybe you can get even more information.
Yeah, certainly that's something that we're interested in doing is, combining several resonators on the same chip.
So the same chip, of course.
One microfluidic channel, and they go through multiple resonators in succession, to give you that more spectroscopic information. Yeah,
because maybe you can detect some molecule with absorption or whatever, kind of a spectroscopy idea. I don't know.
Yeah, and certainly for gas sensing as well. That's ideal, right, where you've got more narrow lines essentially that you can detect. Yeah. Okay,
so it's possible in principle.
Yeah, absolutely.
Okay, we have another question. Very interesting talk. Do you care somehow on the temperature, so to not damage the cell in the issue?
Yeah, that's an interesting question, because when you say microwaves, people think of microwave ovens. So the power levels are incredibly low. So minus 30 dBm or something like that. So even though you're concentrating the field down to a very small volume, your power levels are incredibly small. And in fact, we've done the calculations and there's not much of a temperature rise. But having said that, you could think of an application where you wanted to kill the cell, where you could, ramp up the power, for example, if you found, a cancerous cell or something like that. So I guess there's different options.
Thank you.
Oh, but I have a question there.
Yeah, please.
Sure.
Yeah, what about the field enhancement? Because you are pretty close to the cell wall. So is there any field enhancement around the cell during the application of the microwaves?
I mean, so you've got enhancement due to your metal structure, but the cell itself, it's so small compared to a wavelength. I don't think it's just pretty a homogeneous field, I would say.
Okay.
Yeah.
Thank you. Thank you, Stephen.